So quick review for second law and heat engines, right? A heat engine is something that uses thermal energy, right, to turn it into useful work. And of course, I use cars as my example. And so here again, there's that picture, right? You have a hot side, you have a cold side. The engine is going to do some useful work, and then the rest of the heat is expelled. Hot side would be the hot gases that are exploded within the engine. The cold side is the atmosphere. When I always think about the tailpipe of the car. So here's the guy that I was talking about in the last video, and he's pretty much the father of thermo. And he came up with this idea of the theoretical engine. And he came up with this thing, well, a theoretically ideal engine would have a certain efficiency, right? And so this is just a purely theoretical process. The Carnot cycle will consist of two isothermals, two adiabatic processes. And I don't know how much of this we really need. I'm just going to run through it real fast. So here is the PV graph for this Carnot cycle, that they call it. And this is what happens. Where you have isothermal expansion, and then you have isothermal. Adiabatic, and then an isothermal compression, and then an adiabatic compression. And then this runs through what's going on within the cylinder, and I don't think these things are something that we're going to worry about too much. As far as the graph goes, right, the work done would be that little area inside of that graph, and the net work is actually equal to QH minus QC, which we talked about in the last video. Right? So Carnot efficiency, instead of using Q's, we use temperatures, T. So TH minus TC over TH times 100, and this is the Carnot efficiency. And this is what I usually tell my students that they really need to know, that you might see something where you have to calculate this. I'm not really sure. The AP test has gotten a lot less mathy over the years. Okay, so here again, here are all of our equations. Work is QH minus QC. Efficiency, therefore, is QH minus QC over QH. Right? This is the maximum efficiency. And then when we talk about it in terms of Carnot, we talk about it in terms of temperature, and the temperatures need to be in Kelvin, right? This is not going to happen because what happens is that it would be necessary for the temperature of your exhaust heat to be at absolute zero, which is not something that is possible. Here's a little primer on air conditioners and how they actually try to run the other way. They remove heat, right, from the low temperature side and exhaust heat to the high temp side. And so refrigeration is this mysterious thing. The best example that someone gave me to try to help me understand this is, imagine the heat in your house as a little puddle of water. And what you do is you take a sponge and you sop up all that water with that sponge. And then you take the sponge, you stick it out the window with your hand, and you squeeze all the water outside of the window. And this is essentially the process whereby how our air conditioners cool all of our homes, and how our fridges work. Here's a little practice problem involving an engine. You have a steam engine, you have a hot side, you have something called a boiler, changes water to steam, and the steam drives that piston. That's a picture we've seen a bunch of now. And then you have a cold side. The question is, what is the engine's efficiency if this is an ideal engine, right? So this is what they'll do, is they'll just say, hey, if this thing is an ideal engine, what would your efficiency be? And so we're going to use Carnot, right? There it is. And this is that simple. Math is really easy. You present it as a percentage, right? Efficiency is always, something over something else, output over input, right? And so we're only getting about 40% there. The practice problem. Can you solve this? All right, first step, work equals Q hot minus Q cold. Right? And so what we're doing here is we're actually using the information from this problem that we had just seen, right? So the hot side was at 500, the cold side was at 300, right? And I need to put that on the slide. But anyway, work equals Q hot minus QC. And this is a wonderful little equivalency, I'll call it, that we can use. And you can solve for various things, and this is really handy. And that is an example of a problem. All right, so I'm going to have you guys try this one. You're going to input your answer into Edpuzzle. So we have an expansion of a gas that takes place at 400 Kelvin, and this is how much heat is absorbed. How much heat is rejected by the system during an isothermal compression if the process occurs at 300 Kelvin. Okay, so it's a Carnot cycle, so we can use the Carnot efficiency equation. We have our hot temp, cold temp over hot temp. We can get our percentage, 25%. Now, this engine is only 25% efficient, and they're asking us for how much heat is rejected. So if this is the amount of heat absorbed, 2093, and it's only 25% efficient, then what is rejected? That would be 75. So if we take this and multiply by 75%, this is the rejected heat, right? A lot of cars will probably be something like that. This is an ideal engine, actually, so still not very good, but that's a good example of a problem. Here's a part B. What is the external work performed by the system? Can you figure this out? Remember, it's an isothermal compression, right? So take a look at what happens during an isothermal process. In an isothermal process, temperature stays the same, which means your change in internal energy is going to be 0 because there's no temp change. So Q is equal to W. And the work performed by the system, right? Well, if 75% is wasted, that means 25% was turned into useful work. So the work done is 0.25 times that 2093. And that's the work done by the system. So there's some problems in just taking a look at heat engines and things like this. So I talked in the last video about how there are 3 laws. That was we've looked at the first law. The second law has to do with all of the engines and things like this. Is there a third law? What's the third law? The funny thing is there is no third law. So scientists came up with these first 2 laws, and then somewhere along the way someone went, wait just a dang minute. There's something else that we've known the whole time. That should really be the first law. And they hummed and hawed and said, well, we already have a first law. Should we just change it and call this the first law and then that's the second law? And they said, no, we've already been doing this for so long. And so they did something crazy. And they decided to call the very first law the 0th law. Because we already have a first law. We've already got a second law. We can't just start over. No. Scientists are just quirky people. And so the 0th law is this is an equivalency statement essentially about thermal equilibrium, that if you have a system where you have 3 things, and A is equal to B, and B is equal to C, then that would mean that A is also equal to C. That's all it says. But they decided this should be one of the laws, and so they called it the zeroth law. I thought that I did in this video just looking at a couple problems. And so you have some engine. It has a power output. That's in watts. Power is work over time. Efficiency is 25%, which is probably pretty normal. It expels 8,000 joules of heat. And so you're going to find a few things. You're going to find the heat absorbed and the time for each cycle. So we can write some things down. Power is 5,000 watts. Efficiency is 25%. Our Q cold is 8,000 joules because that's what's expelled. And what we can do is we can use our efficiency equation here to solve for the Q hot. And it looks like QH, come on now, is going to end up being this. So, there you go. That's our Q hot, energy absorbed. Remember, QC is what is exhausted, right? So this is what's left. Q hot minus Q cold equals work done. So we can figure out what our work done is. So there's our work done. We need work done because they want us to find time, right? And that's why they gave us power. And so our work done over time should give us that time if we solve for T. So first we solve for Q hot, then we solve for work, and then we solve for the time. We knew what power was. We found work. It's 0.53 seconds. And so there's a lot of mathiness, and the AP test may not be quite as mathy. Last one. Efficiency of a Carnot engine is 30%. The engine absorbs 800 joules of heat per cycle from a hot temperature side of 500. And they're going to ask us for a couple things. What's the cold side? And the heat expelled per cycle. Carnot efficiency. So we're going to end up doing this. Right? Now, efficiency is work over Q hot, or Q high, or Q absorbed. Right? They told us the efficiency is 30. So that's 0.3. The absorbed heat is 800. That's that hot side. Work done, 240 joules. Now work done is Q hot minus Q cold. So here we go. If we know the work done, we just found, and we know Q hot, we can solve for Q cold. And thankfully we should get something that's less than 800 for our Q cold. It's a Carnot engine. And so we can find the efficiency, we can find the temperature of the cold reservoir using Carnot, because we know efficiency is 30, right? T hot is 500K, and so we can solve for T cold.